Okay, so the last section in chapter 3 is 3.4, which is linear and angular speed. And so this is when you really start seeing some real-world applications to some of the trig that you've kind of already been working through, especially when we talk about radians and things like that. So first, let's talk about linear speed for a second. We use v, which is listed there on the sheet for you, v to indicate linear speed. And really what that is it's how fast that point is traveling on a circular disk, or how fast that central angle in the disk is changing. So if we look at the general picture that they give us here, we have this point P, and it's going to move at a constant speed all the way around the circle. And that speed is the linear speed. Linear means, think of like when you draw a line back in college algebra, linear had like a common slope, so it had a common change that you could watch as you graphed it. So linear speed is going to work the same way. In general, we think of speed as the distance over time. If you want to know your average speed on your drive to Tulsa, you take 100 miles divided by how long it took you to drive there, and you can come up with your average speed. That's not any different when we're talking about angles. We're just going to think about them in a slightly different format now, where v is the arc length divided by time. Because if we're thinking about this point traveling around the outer edge of our circle, then what's happening is it's traveling an arc length, however long that arc length is. And then how long it takes is going to end up telling us this linear speed. And since s is arc length is the radius times theta. So you can think about linear speed as the radius times theta all over the time it takes you. And so it all does come together in the end, which is nice. Now, angular speed is listed with a W. And that's how fast the angle POB is changing. So again, we're looking at the same picture. So it's how fast this theta is changing. It's not how far theta is moving. It's how fast is it actually changing. So W, or angular speed, is always represented as radians per unit of time. So that could be radians per second, radians per hour, radians per minute, or whatever your problem is asking you for. So usually we think of angular speed as W equals theta over T. Again, theta is going to be given in radians. But since W equals theta over T, we can actually think about it like this. If W equals theta over T, then if I multiply that T over, I have theta equals WT. So if I plug that into my angular speed, then I have V equals RWT over T. And then we get this V equals the radius times the angular speed. So we can actually think about linear speed in reference to the radius and the angular speed. What's nice is all of your problems are going to give you every bit of information you possibly could need, except for one piece, and obviously that one piece is what it's going to ask you for. So this was the algebra behind how we can talk about our linear speed being equivalent to the radius times our angular speed. Let's look at a problem. So suppose that the point P on a circle with a radius of 10 centimeters and the ray OP is rotating with angular speed of pi over 18 radians per second. Okay, so I'm going to make a couple of notes. We have a radius of 10 centimeters. We also have an angular speed, so that's our W, equals pi over 18 radians per second. I just like to take notes when I do a word problem so that I can just reference that instead of all the words. It says find the angle generated by P in 6 seconds. So what this first part's asking us for is it's asking us what is theta. We don't know what theta is. But we do know what our angular speed is. Our angular speed is pi over 18. And if our angular speed is theta over t, then what we have is we have pi over 18 equals theta over t. I just substituted in the pi over 18. Whoops, t. It said 6 seconds. So I can go ahead and change that t to a 6. So to solve for theta, I'm going to take pi over 18 times 6. Theta is always going to be kept in radians. So you find pi over 3 radians. That's the angle that's generated by P in 6 seconds. Now, obviously, the angle changes, and so they could ask you for a whole bunch of different measurements, but you do the exact same process. It gave you your angular speed, it gave you your time, you just needed to find theta. B says find the distance traveled by P along the circle in those 6 seconds. So what are we looking for there for part B? If we're finding the distance traveled by P, what is it that we're finding? Yeah, we're finding the arc length. Because remember, the arc length is basically thinking about like the perimeter of a circle. And so we're trying to find what S is for this. Well, S equals the radius times theta. That's your arc length equation. It told us our radius was 10 centimeters. And we found out that in 6 seconds, our theta is pi over 3. So that means we have 10 pi over 3 centimeters. If it wants a decimal representation in your homework or your quiz, it will tell you how many decimal places to round it to and things like that. If it doesn't, then you want to leave it with the pi because that's the most accurate form. Part C says find the linear speed of P in centimeters per second. So linear speed is our V. That's what we're trying to find in part C. And you can use either the V equals S divided by T. You can use V equals R times W. You can use whichever form you want. I went with, what did I go with? I went with the arc length over time because we just found what that is. We found our arc length. We know our time. Actually, it looks like I ended up going with R times W, which is 10 times pi over 18. Because our angular speed is what they gave us up at the top. Up here, this is our W. 10 pi over 18. And that simplifies to 5 pi over 9. And that would be centimeters per second. So writing them with the pi definitely looks weird when we think about doing word problems and leaving it with pi. But again, it will tell you if it wants it in any other format. The problems in the book had it left in pi, so that's why I left my answers in pi. Obviously, theta will always be left with pi unless it's asking you for the actual degree instead of the radians. But as we learned in all of Chapter 3's material, if it doesn't specify that it's in degrees, then you assume that it's in radian mode. So are there any questions on how we tackled any of those questions for this one, where we used a general point P on the outer edge of the circle and we talked about how it traveled around that circle? Okay. Then let's flip over to where we're going to start talking about some pulleys. We've got a belt that's running on a pulley of radius 6 centimeters at 80 revolutions per minute. Part A is asking us to find the angular speed of the pulley in radians per second. So that's asking us for our W. Part B is asking us for the linear speed of the belt in centimeters per second. That's asking us for our V. So it doesn't give us a ton of information, but it actually does give us everything we need. We know the radius is 6 centimeters, and we know 80 revolutions per minute. Okay, so that doesn't give us any type of theta, though. But who knows how many radians one revolution is going to be? Yeah, it's 2 pi. I don't know who's talking. But yes, 2 pi. This is a whole circle. So if we go all the way around our circle, it goes 2 pi radians. Great job. So 1 revolution equals 2 pi radians. So what we know here is we know that W equals 80 revolutions in 1 minute. That's what the problem tells us. But we don't want it in revolutions per minute like this because we need to find out what our W is. And angular speed is always given as radians per whatever the time unit is. In this case, it will be minutes. So you have 2 pi radians for every 1 revolution. And it says radians per second. So right now, what I'm doing is I'm doing a conversion factor. And right now, I would have radians per minute. So that's not what it wants because it wants seconds. So in 1 minute, I have how many seconds? 60. So I'm just doing an old school conversion table. You do these in chemistry when you do like microliters to regular liters or whatever. So then I'd mark out my minutes and I'd be left with radians per second. So 80 times 2 would be 160 pi over 60, which simplifies down to 8 pi over 3. And that is then in the radians per second that it originally asked us for. So I guess the trick for the pulley problem is that it didn't give you a theta of any kind, but you have to recognize that if it's doing revolutions per minute, it actually does tell you how far it's traveling in terms of the theta. Because 1 revolution is like theta going all the way around, which is 2 pi radians. B says find the linear speed in centimeters per second. Linear speed is V. V equals the radius times W. Since we already have the radius in terms of since we already have the angular speed in terms of seconds, I'm going to use that information moving forward so I don't have to do a whole bunch of other conversion factors. So then I go back up to the top and I have a radius of 6. So I'm going to take 6 times the 8 pi over 3, which gives me 16 pi. And this one did have me go ahead and do a conversion to 50. Now you wouldn't know that, it doesn't specify that, which is one of the reasons why I actually hate the examples the book gives, because the examples the book don't give specific enough instructions on how you should put your answer. But that's one of the downsides of the textbook, and one of the upsides of the My Math Lab program is that it is very specific. Next to the answer box, there's always, I think they're green, they might be blue, either green or blue words that tell you what form they want you to put it in. If they want it rounded or if they want it to be exact, it'll tell you to leave it in terms of pi, and so it is very specific. And you will not be questioning what form to leave it in. Are there any questions on the pulley problem? This part right here, the 1 revolution equal 2 pi, that's kind of the trick, like I said, on approaching that problem. Yes, no? All right, let's do one more. Let's do a satellite problem. If you look at my notes, I drew a really nice satellite because I didn't have the picture. So you can marvel at my artwork if you pull that up. It says a satellite is traveling in a circular orbit 1,600 kilometers above the surface of the Earth and takes 2 hours to make an orbit. The radius of the Earth is approximately 6,400 kilometers, and they give you this nice picture. Approximate the linear speed of the satellite in kilometers per hour. So linear speed, that's our V. Okay. Now, what's slightly different about this problem than our other problems is in order for us to use V, what do we need to know? Well, V is S over T, which is R theta over T. Do we know the radius of the circle that is made by the satellite? Because that's kind of where the trick lies. If you just look at it and you say, okay, well, it says radius is 6,400 kilometers, and you figure all that out, what you're actually finding out is what happens if the satellite just goes right around the outside of the Earth. But that's not where the satellite lives. The satellite lives 1,600 kilometers further outside of Earth. So you have to find the radius first by taking 6,400 plus the 1,600, giving us 8,000 kilometers as our actual radius. So we have to be aware that just because they gave us a radius, it's not actually the radius for the satellite. And then we're going to do we got to find W. Because, again, they told us it takes 2 hours to make an orbit. And in this case, one orbit is going to be how many radians? 2 pi. Just like the revolution problem. If you go all the way around the Earth, you're still going 2 pi radians. So if I have one orbit in 2 hours, that means I have 2 pi radians per orbit. And it wants kilometers per hour, so I can leave my hours alone in this case. Meaning that I have 2 pi over 2 hours, meaning I have pi radians per hour. Now I know what my R is. I know what my W is. And V equals R times W. So V equals 8,000 times pi. And again, while this didn't specify, we are going to type that in, and we get approximately 2,500 kilometers per hour. Part B approximates, right there. That's the word to look for. Although that's not applicable up there, but when it says approximate, that's a good word to indicate that you're probably going to end up getting rid of your pi's at the end. That's not how it was in example 2, but that's how it is in this one. It says approximate the distance the satellite traveled in 4.5 miles. So this is asking a slightly different question than it's been asked before. It's not asking us for linear speed. It's not asking us for angular speed. It wants to know how far that satellite's going to travel in 4.5 hours. What we found out here is that in 2 hours, it makes one orbit. So here's what I noted, is that since we know that our linear speed is our arc length divided by time, then we can figure out our arc length by taking our linear speed times time. It's just like traveling in a car. You can figure out how far you're traveling based on how fast you're traveling versus how long you're traveling for. And that's really what's happening here. How far is that satellite going to go around in a given amount of time? Well, we found out the speed. The speed was 8,000 pi. And we know the time is going to be 4.5 hours because that's what they're giving us. So if we know how fast the satellite is going around the Earth, and we know for how long it's going around, we can find out the distance, which is the arc length in this case. You type all that into your calculator, you get 110,000 kilometers. So it's going to travel quite a little distance in that 4.5 hours. So even though we're talking about like distance traveled around the world or distance traveled around a circle, it's really not all that different from talking about linear distance in terms of traveling by car somewhere. It's just we're going it constantly in a circle instead of in a straight line. But the algebra and the math behind it are really the exact same because you're still taking the speed times the time, or you're finding one of the parts of that from the other information that you have.